Okay, we're going to start talking a little bit about the contents of lesson 14. In lesson 13, we talked about estimating the area under a curve. Okay. And area under a curve is going to be a common theme throughout our next several lessons. Another way to indicate that we would like to calculate the area under the curve is through a tool, a notational tool called an integral. So when we write an integral that looks like this, okay, first of all you'll see the big S, which is the integration sign, which is most likely tied back to the idea that we are doing a summation. We're adding a bunch of areas to get this total area. But what we're being asked to calculate is the area under f of x or I guess I'm not going to say above, so area, or let's say area between f of x and the x-axis from x equal a to x equal b. That is the meaning of this integral. So we have some random f of x curve, and we pick a starting point and an ending point, sort of a left boundary and a right boundary. That area is what we're looking for, or what we're calculating when we calculate the value of an integral. Now, what we talked about in lesson 13 was a tool for estimating the area. We would fill this up with rectangles using certain rules, using the left height or the right height, or we might do trapezoids, and that was a tool for estimating areas. Okay. What we're doing today is we're going to calculate areas. And one tool for calculating these areas is to straight up use some geometry. Okay. So certain integral problems, because of the nature of f of x, create an area region that we can calculate the area for. We don't have to estimate it, we can actually straight up calculate it because it's a regular geometric shape. So let's look at some examples of that. And we're going to create some graphs here to help us sort of think through these problems. So my first problem is the integral from 0 to 3 of x dx. Okay, so my function is f of x equals x, or y equals x, which if I graph, looks something like this and extends like that. I want to calculate the area under this curve, but above the x-axis. So that's kind of always an indicator, as a boundary is the x-axis. And we want to start at x equals 0 and go to x equals 3. And so this is actually a really nice problem. It doesn't require any sort of special calculus tricks, because this particular area, this particular region, is just a triangle with a base of 3 and a height of 3 So my area would be 9/2. The value of this integral would be 9/2. Through all of these problems, I am going to use a geometry focus. The first thing I'm going to do is think about that function. So y equals 5. This horizontal line through 5. From x equals 0 to x equals 3. Above the x-axis. And there's our second area problem. I didn't draw that line very well. If I can move it, I can't. So, value of this integral. Area of a rectangle, length times width. Okay. This would be a good point to stop and try graphing the next two problems. You're going to have to think a little bit, maybe use some of your Algebra 2, some of your geometry, maybe just try some table of values. So if I want to look at y equals the absolute value of x minus 2, if I don't remember some things about the absolute value function, I can just try plotting some points. I've got to go up to 5. And hopefully you can get to that. So here is the absolute value function that we're talking about. It's a typical absolute value, but moved to the right 2. I'm going to go from x equals 0 to x equals 5 as my boundaries. Boundary that. So in this case, I've got 2 separate triangles to calculate the area. 1/2 times 2 times 2 for that guy. This guy, 1/2, 3 times 3. So total area, 2 for the little triangle, 9/2 for the bigger triangle, so 13/2. Integrals give us areas. There's going to be lots of different ways we find these areas depending on the shape of f of x. We're going to find other tricks and techniques to let us find these areas, but long story short, every single time we're doing an integral, we are essentially calculating an area. Now, question 4 might take you a while to think through. Oops, it's not a very nice drawing, so I'm going to kind of, still not very good. I'm not a very good sketcher. Okay. This is a half of a circle. Right. We're looking at y equals the square root of 4 minus x squared, or y squared equals 4 minus x squared, or y squared plus x squared equals 4. It's the top half of a circle. So I'm going to take pi times the radius squared and take half of that. So this is going to be pi times 2 squared divided by 2. Final answer, 2 pi. Now, because of certain contexts, because of certain meanings of areas we're going to calculate, it is possible that we may have a negative number to represent an area. I have this in quotes, negative areas, because they're not truly negative areas, but there are reasons why we may talk about a region and use a negative number based on a context to talk about a particular area. Okay, so let me show you one example of this. We're going to look at the function y equals 2x plus 1. So it goes to the y-axis at 1 with a slope of 2, so up 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So here is the line. And the area boundaries, one of my left boundary is -2, my right boundary is 3. Here is my x-axis. So what's going to happen on this problem is I'm going to have that area under the x-axis, and then I'm going to have this area above the x-axis. Now, we're going to talk about this a lot of different ways in different aspects of this unit. For today's lesson, we're going to talk about going from, if we think about starting at a -2 and ending at a 3, that section under the x-axis is going to represent a negative area, where the section above is going to represent a positive area. So my little triangle, the -1, is 1/2 times 1 times 2. My positive triangle is 1/2 times 4. Oops, hang on a second. Let me back up here. My picture doesn't look great. Let me make my picture a little nicer. Back it up. Back it up. All right. So at -2, oh, because that's that line. Okay, up 2 over 1, up 2 over 1, up 2 over 1. Yeah, okay. So here's the thing that's a little tricky about this one. Where it crosses the x-axis is not at a whole number. 2x plus 1 equaling 0 is what we're talking about when we cross the x-axis. And that's going to be at -1/2. So this point right here is -1/2, 0. So this triangle, my negative triangle that I have in purple, is 1/2 times 3/2, 1.5, that's this section, times 3. When x is -2, y is -3. This is 3 units down, and it's 1.5 or 3/2 across. So this negative value is going to be -9/4. God, I caught that before I went too far. Now this piece, I'm going up to 3. Okay. At 3, this is going to be up at 7. So the positive triangle is 3.5. So 1/2 times 7/2, because it's 3 whole units and another little half, times 7. So that's going to be 49/4. So the total value of the integral is going to be 10. You're definitely going to probably want to go back and look at that more than once to kind of figure out, okay, first of all, the idea that I've got two triangles, that one of them is going to represent something negative versus something, and then the other one's positive. I think we can see that. The figuring out of that value to make this full calculation is a little tricky because it's not on an exact whole number. We have to think it through a little. Figuring out that that's -1/2 helps me figure out from the -2 to +3 the 5 units across this is, that 1.5 of them, or 3/2 of them, are on the purple triangle, and 3.5 of them, or 7/2, is on the red triangle. Definitely something to go back and take another look at. You're only gonna, well, for now, the only way you'll know that this is gonna ultimately come out to worry about having a negative section plus a positive section is because you're gonna graph it. Number 6, a little easier, y = -3 is this horizontal line right here. From a -2 to a +3 with my x-axis right here. So all of my area from what we're going to consider, oops, let's not write in highlighter. Let's not write in anything crazy. Okay, so this is my start, the -2. This is my end. This is 3. If I'm going across like this, this is all under the x-axis, so it's all negative. So this is -5 times 3, -15. Okay. Our first plan of attack on calculating the value of an integral is potentially to use the concept of an area. An integral does represent an area, and geometry might be the key to that area.